So let me show you what's up here. So in 13.8, we're talking about, the title is, Extrema of functions in two variables. So yeah, mins and maxes of these 3D surfaces. And so first though, we need the candidates for mins and maxes. The good candidates to be a min or a max are these critical points. And so the definition of a critical point in 3D is this. So x naught, y naught is a point, is a critical point of some function f of x, y, if, and here we go, the definition of a critical point, if the partial derivative with respect to x at that point equals 0, and the partial derivative with respect to y at that point equals 0. Now we've sort of previewed this idea already. We were looking for these places. There were some preview questions as we did partial derivatives in this chapter. There was a couple preview questions that said, please find the places where your fx and your fy both equal 0 simultaneously. And anyway, at the time maybe we didn't know it, but we were looking for critical numbers, because when the partial derivative with respect to x and the partial derivative with respect to y both equal 0, that means you're probably at a max. Or you're at a min. I mean, you have a slope of 0. By the way, if the fx and the fy are 0, that means the duff is 0. So that means the slope is 0 in any direction. So you're probably sitting at a max, at the top of a hill, or at a min, the bottom of a valley, or neither a max or a min, but just sort of a level place, which they call a saddle point. So, right, we're either at a max or at a min. This is supposed to be in 3D. It's not the best 3D picture, but at a max or a min, that's even worse. Or a saddle point, which is kind of hard to draw, but we've described it before. We've described there was a shape. I called it a saddle. It was actually called a hyperboloid. An elliptic hyperboloid, I believe. Anyway, it's like a saddle. You know, in one direction it does look like a min, but then in the other direction it might kind of look like a max, depending on how you're looking at it. It's really neither a min or a max. We call that point right where your butt sits on the saddle a saddle point. Neither a max or a min. So anyway, in 3D, max, min, or saddle point. That's what these critical points could be. Well, first we look for critical points, and then they could be a max, a min, or it could be a saddle point. Now wait a minute, just to complete the definition, this is typically where we go. We look for where these partial derivatives are 0, but there is the other option where the partial derivative might be undefined. And it's either this one or this one is undefined. It's kind of important that this word and is here. It's not just where he equals 0 or where he equals 0. It's this simultaneous thing. It's where him and him both equal 0 at the same time. That word and is kind of important there. And then there's also the other possibility where they're either one is undefined. Yeah, that I don't think will come up too often, but technically it's part of the definition of a critical point. So, cool. So we need to practice finding a critical point. But then what? So then after you find a critical point, it could be a min or a max or a saddle point. And there's this special test in order to figure this out. And it's called the second partials test. The second partials test. Now I'm going to write it up here today, and then we'll practice trying to use it. But the truth is, I'm going to give you this on test day. You have to memorize some formulas for this chapter. The duff, the gradient, the total differential. I mean, you got to know some formulas for this chapter, but not. And you might need to know this, how to get a critical point. But you don't need to have this memorized. I'm gonna share this with you. What is this thing? It says, so what you do, you take your critical numbers. Let me see what this says here. You find your critical numbers, and then here's what you do for the second partials test. You calculate this number D. How do they write this? Yeah, okay, all of a sudden now they change their notation. They say your point A, B is a critical number, is a critical point. So instead of X naught, Y naught, they use A, B all of a sudden. So now what do you do with your critical point? You calculate this number D. Check this out. The number D is, and it's the second partials that I use. Why? So it's fxx. And you know what that is, I guess, but we haven't done it much in this chapter, but it was introduced. This is the second derivative with respect to x again. You do the derivative once with respect to x, you do the second derivative with respect to x. Anyway, evaluate that second derivative at the point AB. Multiply it by fyy evaluated at AB. And subtract what you call the mixed partial, fxy evaluated at AB. But hang on, that thing is squared. You find your critical numbers, and then you perform this calculation. And you calculate this number D. And now here's the conclusion. 1, 2, 3, or 4 here. Here we go. If D is greater than 0, and that fxx right there that you use to help calculate D, if that is greater than 0, then we just discovered that our point AB is a relative min. Hope I did that right. Let me just check myself. Is that right? If he's positive and he's positive, then it's a relative min. Right. All right, let's keep going. If the D is greater than 0, but while you were processing that fxx was less than 0, okay, then it's a max. Then that point AB is a relative max. Again, I'm writing it all up here today. I'm going to give you this. I'm going to copy it out of a book and give it to you on test day or something, or write it on the board again or something. But here's what happens. Here's another thing that can happen. What if the D is less than 0? So both those cases, the D was positive. If the D comes out negative, though, you're done. It's a saddle point. That AB is a saddle point. That point AB, that critical point, is a saddle point. And finally, if D actually comes out to equal 0, this test is inconclusive. This test is inconclusive. So now, that means I don't know if it's a min or a max, or I don't know what it is. That rarely happens to us. I like regular problems that have answers. That's it. Hey, that's 13.8 in a nutshell. We find critical numbers and we test them to see if they're mins or maxes or saddle points. And so that's it. I mean, I need to practice a couple problems. By the way, here's what 13.9 is. 13.9 is word problems that are maxes and mins. So, good luck. You read the word problems and play the same game. Now, I'll help you with some of those. But what I'm saying is, in a way, it's not a new topic. 13.9 is just word problems of maximizing and minimizing in 3D. Okay, I want to try a problem. In 13.8, if I just find a problem, and I didn't assign too many of these, I really like the good ones, and sometimes some of these are just kind of boring. I mean, I like to find a lot of critical points. I wonder what would happen. Some of these don't have too many critical points. That might be kind of fun though, maybe 14. Let me try 14. So I'm in 13.8. I just picked a problem, 14, and it's a function. It's z equals, or I'm going to, but of course z is f of x, y, f of x and y. Negative 5x squared plus 4xy, negative 5x squared plus 4xy, I'm sorry, minus y squared plus 16x plus 10. Minus y squared plus 16x plus 10. All right, there it is. Dude, I don't know what that is. That's something. I don't know. It might have mins and maxes. It might have saddle points. I have no clue, but I can figure it out. What I should do first is look for critical numbers. In order to look for critical numbers, the critical points, it's the key is this. The key is this. So I'm looking for when these things equal 0. So let's get fx. So fx, I'm just switched notation here. Maybe I should have called it zx, but it's okay. We know what we're talking about. The partial derivative with respect to x is
negative
10x
4y plus 4y plus 16.
Plus 16. That's what it is. The partial derivative with respect to x. Cool. Let's go for the I need the partial derivative with respect to y also. By the way, that's kind of what you need all chapter. You need this kind of stuff. Here we go. Partial derivative with respect to y. I guess that's a 4x minus 2y. I think I'm done. Okay, so again, this one's going to be kind of easy. So now we set both of these equal to 0, and really it's kind of like negative 10x plus 4y plus 16 equals 0. Also, the 4x minus 2y equals 0. And all of a sudden, it's kind of like solving two equations, two unknowns. You're back to algebra, and you're sort of solving two equations, two unknowns. You are. There could be multiple answers, though. I think this one will only have one answer. When you're solving two equations and two unknowns, you got a lot of methods at your disposal. Usually, substitution is sort of a good method. I think I'll solve, I'll move this 2y over. 4x equals 2y. I'll divide by 2. Y equals 2x. I'll take that and substitute it for y. So I'll have negative 10x plus 4 times y, which is 2x, plus 16 equals 0. You guys know the game, right? That's negative 10x plus 8x. So that's a negative 2x plus 16 equals 0. Move the 16 over, maybe divide by negative 2. I think I get x equals 8. Sorry, I got myself into a corner there. X equals 8. That's just the x value. You could go back to this equation. When x is 8, y is 16. They go together. You know, these critical points they're ordered pairs, you know, from the domain of the function. They're ordered pairs, so it's really 1 point, 8 comma 16. That's my critical point. Cool. Okay, I'm going to get rid of this little note here. And so that's my critical point. So here, again, it could be a min, could be a max, could be a saddle point. Yeah. And so I want to, this is the place where the slope is 0, yeah. So to calculate which one it is, I got to do this test. In order to do this test, it's really about calculating this number b. Well, it's about these conclusions here. But I need to calculate this number b, which requires me to do all these second derivatives and evaluate these second derivatives at my critical number. So I need these second derivatives, and then I need to kind of plug this in. Now, what's funny about that is these are going to be boring little second derivatives, I think. Watch. What is fxx?
Negative 10.
Negative 10. And again, I'm supposed to plug a point into there. Well, you know, there's nowhere to plug a point into there. So when I do plug the point in there, its value will be negative 10. I need fyy. Fyy. Negative 2. And then I'll plug a point in there, but I can't plug its value will be negative 2. I also need fxy. Fxy.
4.
4. Good. And then my number D, again, it's kind of weird, with no variables in here. I'm supposed to plug the point in here, but with no variables in here, these just have these values, and I get my number D. My number D is the fxx times the fyy minus that fxy squared. And the value of that is 20 minus 16, 20 minus 16, or 4. So the D is a 4. So the D is positive. Okay? If the D is positive, it could be a min or a max. What I'm supposed to do is look at the fxx. When I plugged in the point, was it greater than 0 or less than 0?
Less than 0.
Well, my fx was just a negative 10, and that's less than 0. Good. So my D was positive, my fxx was negative, therefore, this dude's a max. Awesome. He's a max. So the conclusion is, right, the point 816 is a relative max on this function. You know, I just listed this as the answer. I mean, it was my critical number. My critical point was 816. And I did the test and discovered it was a max. So there I am calling it a max. Sometimes, I mean, I don't know how picky I'll be or how picky the book might be, but, you know, when you write this point, it's a point, but it's actually just a point from the domain of the function. I mean, it's a point that lives in the xy plane. If it's actually on the surface, then of course it's a 3D point. I mean, you know, it's got a z value, and if you wanted the z value, how would you get it?
You take the partial derivative.
No. So this is a point on the function. It's a point on the function, and it's a max. But 816 is the x and the y coordinate. If I wanted to really list it as a point on the function, I feel like I need the z value. How do I get the z value? The z value of a point.
Plug it in and solve.
Just go back to the original function and plot it. Plug it in, I guess. I don't mean to be confusing you. Am I confusing you?
No.
I'm just saying, we are in 3D. Our points are 3-dimensional points. If I want the z value that goes with this xy, then I plot it. But that's a bit of a pain in the ass. I mean, it's, excuse my language, right? It's negative 5 times 64 plus 4 times 8 times 16 minus 16 squared plus 16 times 8 again, plus a 10. Right, I'm plugging in that point. I can find z and list it maybe more appropriately. Good God. Maybe you guys can beat me. Maybe I can beat you. Let's see what. I might have got off track. 202? I'm getting a 202, but I might have got myself off track. This is negative. What did I do? I did.
I got 586 total.
Okay.
Yeah, that's 512. After 80 means 54 times 8 times 16.
Right, that's 512. Minus this 256 here. You know what that is?
Yeah.
Plus this.
16.
Maybe I was sort of right.
128
I
and
think you might have added the 16 squared instead of subtracting.
oh
Yeah,
yeah,
we are subtracting that.
yeah, I accidentally did negative 16 squared. So yeah,
So maybe I'm right.
I think so.
Wow, it's a miracle. A Christmas, a Halloween miracle. All right. Anyway, I mean, it's just a small detail. My point is, if it's a point on the graph, it has 3 coordinates. But it's a max. I mean, it's almost like you should talk like this. This is the actual max where the point lives. This is sort of where it occurs. The max occurs at the point in the domain called 816. On the actual function, it's 816,202. It's got this e value. Anyway, again, that was kind of an easy one. One critical number, little linear functions here, no squares or cubes. I mean, so it was a little easier, but it's good. You got the point across, perhaps. There's some of this stuff on my my take-home thing and on my practice thing. There's some of this stuff, so there's a good place to look for more. Here's one. Let's try this 18. Let's try this one. All right, I'm going to start over here and give myself some space. Number 18 out of the book. One thing cool about 18 is there's a picture of the function, so I can kind of see where I'm headed. But the function itself is 2xy minus 1/2 x to the 4th plus y to the 4th plus 1. Wow. It is 2xy minus 1/2 x to the 4th plus y to the 4th in parentheses plus 1. That's kind of interesting. I should just distribute that half actually, but we'll deal with it here. Okay, there it is. We'll deal with it. Here we go. Step 1, I'm looking for critical numbers. And so to get critical numbers, I need the first partial derivatives. Fx is 2y minus, so that's a 1/2, and then I can just take the derivative of the x to the 4th, which is 4x cubed, times that. Anyway, I could have thought of it as a 2x cubed. That's what it is. The derivative of y to the 4th is nothing. The derivative of the 1 is nothing. So there I am. That's a 2. Right, you guys? 1/2 times 4. All right, that's that. What about my fy? Oh, it's kind of similar in a way. Fy is taking the derivative with respect to y. It would be 2x
minus 1/2 4y cubed
times 4y cubed. Yeah. All right, well, then I'm setting these equal to 0. You know, I can sort of do it like this, but yeah, let me get a little more organized here. Let's see, I'll come down here. That 2y minus, this is 2x cubed. All right, so that equals 0. You know what, I think I'll solve for y here. Watch, I'll move the 2x cubed over. Yeah, I'll divide by 2, so y equals x cubed. Okay, my other equation is right here, which says that 2x minus 2y cubed equals 0. What am I going to do then? I'm going to substitute this in here. I'm going to substitute this in for y. Wow, check this out, you guys. 2x minus 2y cubed, but my y is an x cubed, and it's going to get cubed. I don't think I've ever dealt with a 9th degree equation before, but this is a 9th degree equation. This is 2x minus 2x to the 9th equals 0. Cool. I knew my algebra would come in handy someday. X to the 9th. Do you know how to solve that equation? Factor.
Could factor a 2x out?
Factor out a 2x. Factoring out a 2x, then I'm left with 1 minus x to the 8th equals 0. I set the 2x equal to 0, and I get x equals 0 as one of my answers. I set the 1 minus x to the 8th equal to 0, and maybe I move the x to the 8th over and take the 8th root of both sides. And you know how algebra works. When you take the 8th root of both sides, or any even root, you should do a plus and minus. So x is plus and minus 1. Now what's important is we just found 3 x values, and now I need to find the y values that go with them. Now that's important. You got to find the y that goes with the right x. It's not just a bunch of x's and a bunch of y's. I mean, when x is 0, go back here. When x is 0, what is y? 0. But that y goes with that x. And that's one of my critical numbers. When x is a 1, what's y? We'll go back here. When x is 1, y is 1. And when x is negative 1, what is the y that goes with that? When x is negative 1, you cube it and you get a negative 1. Y is negative 1. So you got to put the right y with the right x. Of course, it comes from solving the equations, but we need the right ordered pairs together. That's pretty good, dude. I got 3 critical numbers. Well, I better test them. These are my 3 critical points or critical numbers, whatever. And I better test them. All right. In order to test them, I need this test here, and I need my second partials. So I need a little more board space here. Let's see. I need fxx. Fxx. Now, here's fx. So that means I got to do this derivative with respect to x. All right. I guess that's gone. And keep in mind that's a 2 or negative 2. So that would be 6x squared, negative 6x squared. Do you guys agree with that?
Mm-hmm.
6x squared. Okay. Fyy. I need Fyy. Okay. Fyy. Right here. Fy. Now take this derivative with respect to y. That's gone. This is a negative 2y cubed, so it'll be negative 6y squared. Yeah, negative 6y squared. I also need fxy, which we call the mixed partial, where we go back up here and we take the derivative of it, the one, we do x first and we do y second. So here's x, here's the derivative with respect to x. Now take this derivative with respect to y. That's kind of cool. 2. All right, now I have to sort of work on these, each point sort of separately. First we're going to check out the 0, 0. So we're checking out the 0, 0, and I have to calculate my d. My d is the fxx evaluated at that point, the fyy evaluated at that point, minus, multiply together, minus, so here we go. Plug that into the fxx. Well, if I plug that 0 into the fxx, I get 0. If I plug that 0 into the fyy, I get 0. This time I'm plugging in the y for 0, but I still get 0. And then I have to subtract what happens when you plug that point into the fxy. Well, you just get 2, and you subtract 2 squared. Now look what we just got here. That's a 0 minus a 4. That is a negative 4. And what does the second partials test say?
It's a saddle point.
When d is negative, it's a saddle point. Cool. Cool. He's a saddle point. I can list. We're done. We've reached that conclusion. He's a saddle point. Okay, next, we'll do the 1, 1. Let's do the 1, 1. Here we go. D equals. Okay, I'm plugging in the x and the y are both 1s. I'm plugging it into the fxx, and I get a negative 6. I'm also plugging both those 1s into the fyy, and I get a negative 6. Minus, I also plug those 1s into here, but I just get a 2. And it is a 2 squared. Well, cool. That's 36 minus 4. That's a 32. So the d is positive. If the d is positive, you better check out the fxx. Was it positive or negative? It was negative. So with the D positive and the fxx negative, it's a max. Cool. These are relative max. All right, one more. -1, -1. -1, -1. Putting him, checking him out with this D, doing this D. Plugging the -1, -1 into there, you still get a damn -6. Excuse my language. And when you plug it in there, you get a -6. Okay. And then you subtract 2 squared, and so you get 32 again, which is positive. The D is positive, but the fxx was negative. That's another max. He's another relative max. So, we're done. We're finished. Let me ask you a question. I'm saying I'm done, I'm finished, but there's one thing I did last problem that I didn't do this problem. What would that last one thing be?
Find the Z.
Yeah, actually, if I'm going to list these officially for my picky professor, perhaps he wants the Z values listed. Well, that means you got to go actually plot these points, which is not that hard, but I'm just going to, maybe I'll do that as quick as I can here. Let me see. So I'm going to make myself have a little Z value there. And if I take 0, 0 and plug it in there, 0, 0, 0, I think I get 1. So that's where my saddle point is. If I plug 1, 1 in there, I get, that's 1 plus 1. So that's 2 times a half, that's a 1. Plus that other 1, those are gone. I think that's a 2. And if I do -1, -1, I believe it's very similar, yeah. Yeah, that's also a 2. Cool, that was easy. Those were easy Z values. By the way, this 18 had a picture. You guys might not have a book, but that's what the picture looks like. It was kind of a... it's hard to draw. But at the point 1, 1, there was a max here. There was a little hill here. There was a little valley in here at 0, 0. But it wasn't a min. Why wasn't it a min? It was a saddle point. Yeah, just because of the way it looked. And then back there at -1, -1, which is back here, there was another little hill. Now again, this is in 3D, dude. This is kind of hard to draw. It's kind of sloped. There's kind of like 2 peaks of a mountain here with a little valley in between them. But then, how come we don't call that valley a min? Well, it's a saddle point. The math told me it was a damn saddle point. It also looks like a saddle point, right? Maybe, I mean, it's not a min. A min would be not a valley like that, but an actual bottomless pit. Well, not bottomless, but... all right, that was fun. You know what I'm going to do then? I'm going to take you into 13.9. And so 13.9 is the same game, but it's word problems. And the word problems can be actual interesting word problems, or sometimes they can be very mathy. I mean, it just depends. But let's do a word problem quickly before we quit. I mean, and there is a few differences in the strategy here, actually, but it's, so 13.9 is max-min applications, optimization they call it. What do they call it? Applications of Extrema. There are some tough ones here. There can be some tough ones. And they do a lot of these abstractly. All right, I'll tell you what I'm going to do. I like this number 9, but I hate to steal your homework from you. So I'm going to do number 9, and I'm going to change the numbers. So number 9 modified number 9. You ready? Let's see what it says here. It says, a home improvement contractor is painting the walls and ceiling of a rectangular room. All right, hold on. I gotta see what this looks like. A rectangular room, that's not necessarily a square, not necessarily a square. It's got walls and a ceiling. Jesus. If I built this room, it would kind of look like this, probably. Out of whack. All right, so walls and ceiling. He's not painting the floor, that makes sense. Okay, he's painting the walls and the ceiling. The volume of the room is 668.25 cubic feet. All right, I'm just going to change it. I'm going to say the volume of the room is 900 cubic feet. I'm just changing it. The cost of the wall paint is a 0.06 per square foot. Just 6 cents a square foot, I think they said. So hang on, the cost of wall paint. All right, I'm going to change that to 8 cents per square foot. That's the cost of the wall paint. What else do they say? The cost of the ceiling paint is more, 11 cents per square foot. Okay, so the cost of the ceiling paint is a little bit more. I'm going to call it, I'll call it 15 cents a square foot. Okay, I'm changing the numbers a little bit and see what happens. Find the room dimensions that result in a minimum cost for the paint. Jeez. All right, so I want to minimize cost. I want to minimize cost of paint. Well, you guys, let's see here. I need to... So what we were just doing in 13.8 is we were minimizing or maximizing a function, finding the mins and maxes of a function. Well, I need to create myself a cost function. Well, so this is the word problem aspect of this, is you got to think your way through this. I would probably say that the dimensions of this room are x by y by z. That makes sense, I think. And they're not necessarily, nobody said it was a cube or a square or anything, so x times y times z. Now, let's see. So what would be the cost of painting the walls? Well, let's see. I guess the cost of painting the walls is 0.08 per square foot. Well, how many square feet do I have? How many square feet do I have for the walls? Let's see. What is the square foot of this wall? It's y by z. It's y wide and z tall. What's the square foot of this wall? Y times z. And then there's another wall on the opposite side that's the same square. So there's two YZ walls. And what's it going to cost? 8 cents each. Or 8 cents for each of those square feet. Now that's not all the walls. Here's some other walls. Here's a wall right in front of me. What's the dimension? What's the square footage of this wall?
It's XZ.
XZ. And there's two of those. So there's two XZ walls, and their cost is still 8 cents per square foot. See, I guess I'm calculating the square feet, and I'm multiplying it by 8 cents per square feet. I mean, if you think about the dimensions here, the square feet are going to cancel with the square feet, and this will be cost. And this will be cost. And now I need the ceiling. What are the square footage of the ceiling? Well, it's a lot like the floor, except, yeah, we're not painting the floor. It's x by y. It's an x by y, and there's only one ceiling. So it's x times y, and then the cost for the ceiling is 15 cents a square foot. Cool. This is my cost equation. Now check this out. Again, we're in this word problem setting. This is the typical. It's very typical for this to happen. So we went to the trouble of developing our cost equation, and I want to minimize it. And I know how to look for minimums. I take the partial derivative with respect to x, I take the partial derivative with respect to y, and I set them equal to 0. Now hold on. When I stare at this equation, I got z's in here. I mean, what I got is too damn many variables. See, what I learned in 13.8 was how to maximize and minimize a function of two variables. Well, a three-variable surface, but a function of x's and y's. And I got a function of x's, y's, and z's. There's too damn many variables. This is typical of these problems. There's too many variables. Is there some other piece of knowledge that would help me get rid of z? I need to get rid of z. Do we have another piece of knowledge? Oh, the volume of the room was 900. And the volume of the room is, x times y times z. So that's 900. So maybe I can, solve for z. What is z? Z is 900 over x times y. That's what I need. I'm going to use that piece of knowledge to replace these z's, and then I'll have a function of x's and y's. Here we go. Let me do a little cleaning here. Let's see, that's 0.16 y, and I'm replacing the z with 900 over x times y. Is that what I'm doing? Yeah. What am I doing here? That's a 0.16 x, and then I'm replacing the z with 900 over x times y. Over here I just got a 0.15 xy. Okay, we're getting there, you guys. We're getting there. This is a word problem. You got to fight through the words and the geometry a little bit. It's pretty easy geometry, dealing with this rectangular room, rectangular solid. I'm going to clean this up just a little more. This cost equation is turning into, maybe you could help me. What's a 0.16 times that 900? Oh, and by the way, the y's cancel. 0.16 times 900.
144.
144?
Mm-hmm.
144 over x. So the next one is going to be 144 over y. And then finally, this is a 0.15 x times y. Yeah, look what I got. I got a cost function with just the two variables x and y. And that's going to be a max or a min if I can find critical numbers. And how do you find critical numbers? You do cx and you do cy and you set them both equal to 0. Here we go. cx. Cx. You know how to do that one?
Could you bring the x up into the numerator?
Yeah, you have to. Yep. And then it's x to the negative 1. Then you just do a power rule, and you get negative 144 x to the negative 2. Or if you don't mind, yeah, that's how you do it. Take that derivative with respect to x.
That's negative 1.4 over.
Well, wait a minute. With respect to x.
Oh, right.
It's gone. He's gone. And then over here, with respect to x, I get a 0.15 y. All right, that's one of my equations. I'm going to set that equal to 0 in a minute. Let's get the other one. cy, the partial derivative with respect to y. This term goes away, and this term is kind of same idea. Negative 144 over y squared, and then a 0.15 x, I guess. Yeah. All right, cool. I'm setting these both equal to 0 and solving this simultaneous set of equations here. Looking for critical numbers. Okay. Let's see. I guess let's see. I think I'll do this 0.15 y equals, I think I'll move this guy to the other side. He'll be a positive 144 over x squared. I'll divide by 0.15, so y is, what is 144 divided by 0.15?
160.
Cool. Yeah, that's cool. So when I divide by the 0.15, I get a 960 over x squared. That's y. What should I do with that y? I guess I should plug it in for this y. All right. Negative, and oh, by the way, I'm setting this is set equal to 0 here. 144, this y would be that 960 over x squared, plus 0.15x. All right, well, maybe I can solve for x. Or maybe I can't. 960 squared. Yeah, I guess. So that's negative 144 over.
Got 921,600 over x to the 4th.
Yeah, 921,600 over x to the 4th. Plus this 0.15x. Okay. All right, do you know what to do? Flip this up. And if you flip this up, I mean, I don't know, there's a couple of different ways to talk, but if you're dividing by a fraction, you multiply by the reciprocal of that fraction. So that means you flip it up, which means the x to the 4th ends up on top, and the 921,600 is still in the bottom, kind of. So now I wonder what 144 divided by that is. 144 divided by that.
Got negative 1 over 6,400 when you reduce it.
Really? Thank you. Right, I'm getting a little nasty decimal, but you're saying 144 over 92,600 is
Negative 1 over 6,400.
negative 1 over 6,400. Okay. Thank you. 1 divided by 6,400. Yeah, you're right. Okay, cool. That equals 0. This is a 0.15x. All right, you guys, what am I doing now? More algebra. It's just algebra. Factoring out an x, maybe? Factoring out an x. If you factor out an x, then you have negative x cubed over 6,400 plus 0.15. And when you set this equal to 0, you get x equals 0. You know, x equals 0 would not be much of a room. That's the kind of room I would like to paint. It's got no width. So that's not really a legit critical number. We're going to throw it. It's a critical number from the math. In the context of the word problem, we'll throw him out. The other critical number we're looking for, oh, the truth is, by the way, that x equals 0 probably makes me have a minimum cost because there ain't no room, right. So, we're looking for, no, I'm sorry. I said that wrong. We're looking for minimum cost. X equals 0 just doesn't make sense. Anyway. So this will be it. Whatever I do here, what am I doing? Negative x cubed over 6,400 equals negative 0.15. Multiply by negative 6,400. X cubed would be whatever 0.15 is times 6,400. Really, back to that number. I knew that we were going in circles here, sort of. Not exactly. 960, cool. So guess what x is? The cube root of 960. It's not pretty, I don't think, but it's a number. You can decimalize it. The cube root of 960.
Got 9.865.
Okay. Approximately 9.865.
Yeah.
Cool. That would be the x dimension of the room that would minimize cost. How do I get y? Where is y? What did they want? I better read this question again. The dimensions of the room that minimize cost. Okay, so all I got right now is x. I should be able to get y. Where's my y? Oh, there it is. We're into a little overtime here, but maybe you don't mind. So y is 960 over this x squared, which means it's this cube root squared, which kind of means it's 960 to the 2/3 underneath a 960. Guess what this is? This is also the cube root of 960. That's what this is. It's a 960 divided by a 960 to the 2/3. You get a 960 to the 1/3. It's the same thing. It's the same thing. Which I think makes sense because the walls, they didn't say different walls were different costs. All the walls were the same cost. So that kind of means that the x's and y's should have the same dimensions, I think. Yeah, cool. We got a couple of dimensions. Hey, what if I want z? Where the hell is z? Where the hell is z? Oh, there's z. So z would be that. That'll be a different number, I think. That'll be a different height. Z will be 900 over the cube root of 960 times the cube root of 960, which is the cube root of 960 squared. But this time it doesn't cancel quite like the last time. Maybe you could just decimalize that for me. Roughly the same. Or you could call it 900 divided by these numbers.
Yeah,
Right.
9.248.
What'd you say?
9.248.
Okay, 9.248. All right, I trust you. You know what? We did it. We found the dimensions that minimize the cost, I think. Listen, it is time to go. I want to point out something. At the end of this problem, notice what we didn't do. So we're up here in 13.9. We're doing word problems. We set the thing up. That's the hard part of the word problem is setting up your equation, maybe. You take your first partial derivative so you can find your critical numbers. But then, you know what I did? I never proved to you that my critical numbers were maxes and mins. I didn't go do this. Well, listen, because usually here's what the deal is. In a word problem, you're going to go through all this work. You're going to find, they're going to ask you to minimize something. You're going to find one critical number. It's the minimum. You don't have to prove that it's a minimum to me. So now if you happen to find two critical numbers and you're debating, well, then maybe you better decide who's a min and who's a max. But usually these word problems they ask you to maximize, your one critical number you get is the answer. Or if they ask you to minimize, the one critical number you get is the answer. So you don't really have to prove it at the end to me. That was fun. That's a classic, man. They've done different problems with dealing with rectangles like that. And it isn't just about paints and cost, but it's kind of this classic math going on here. So that's a good one. You could try number 9 again with the numbers in the book. I'm going to quit. Thanks for listening. And I'll see you Friday. Answer all kinds of questions. I don't feel like I got too much new to teach you.